I am pleased to welcome you to today's webinar. It is entitled, Understanding Deep Borehole Disposal Technology in the Context of Spent Fuel and High-Level Radioactive Waste Disposal. We are pleased to welcome you for a two-day webinar, and it is provided to you by the International Framework for Nuclear Energy Cooperation, Reliable Fuels Nuclear Working Group. I am Alicia Duncan, the U.S. Steering Group Chair. It is my honor and pleasure to welcome our distinguished panel today, who have been brought together at our request of the RNFSWG co-chairs, Sean Tyson and Thomas Segar. I'm excited about this topic and glad that you all could join us today. Without further ado, I turn the floor over to Thomas Segar. Thank you.
Thank you, Alicia. Thank you for this kind introduction. My name is Tomáš Žágar. Sean Tyson and I serve as co-chairs for the IFNEC Reliable Nuclear Fuel Service Working Group, the sponsors of this webinar. We are pleased to welcome you to this two-day webinar as one of many activities IFNEC offers to its members. IFNEC is dedicated to promoting cooperation on the peaceful uses of nuclear energy, and the working groups provide specific events and activities that support that mission. This webinar is an example of the value that IFNEC brings to its member countries. In July, the working group sponsors the webinar on multinational repository concept. You can find the recording of that webinar on IFNEC website, along with the slide presentations and questions submitted with answers. The same will be provided for this webinar too. In this webinar, we will explore a disposal concept that has received varying levels of attention over the years and has recently seen the development of specific technology evaluation projects and commercial interests. Disposal of spent fuel and high-level radioactive waste in deep boreholes is currently the only alternative to a deep geological repository. It appears possible that this technology could serve to complement the repository approach and is therefore relevant to our work on multinational repositories. As we are currently in the early stages of the development of this technology, the working group concluded that it is an excellent time to provide IFNEC members with an understanding of both the promise it presents and the challenges it faces. You will hear from both the prominent international experts on deep borehole disposal and also those involved in projects to develop the technology. To the extent the presentations leave you with further questions, we encourage you to submit them to be addressed by our experts with responses published following the webinar. I will end my introduction with warm welcome to Moderator, Neil, and all panelists, and to Robert Masler from the Technical Secretariat that helped put this program together. With that, I will hand the program over to our moderator, Neil Chapman, to introduce himself and begin the program.
Thank you very much indeed, Tomáš. My name is Neil Chapman. I'm going to be moderating today and tomorrow. My background is in geology. I have been working on deep geological disposal of radioactive waste for about 45 years now, and I've worked internationally in most programs around the world. I began in the United Kingdom on the program back there in the 1970s, and then I moved over to Switzerland for a while, and I've been involved in various aspects of safety case development, siting, and so on. Latterly, I've been particularly interested in multinational solutions that Tomáš just mentioned as being one of the recent webinars that IFNEC has organized. So I'm working through the Arius Association and the ERDO working group on potential shared multinational solutions. Over the years that I've been working on this, I've always had an interest in deep borehole disposal. It is a topic that hasn't been as well developed as what I might call conventional deep geological repositories, but it has certainly got potential, which we're going to explore over the next couple of days. If we could have the first slide, please, as an introductory slide here. For those of you who may be not quite so familiar with what we're talking about, this slide here just tries to put into context what it is that we're going to be discussing. If you look over on the top left-hand corner, you'll see deep geological repositories. These are things you're probably familiar with. These have been developed all around the world, depths of 300 to 800 meters typically, and they're designed for long-lived and intermediate level wastes. And then over towards the middle, we've got much deeper solutions, and that's what we're going to be discussing over the next couple of days. So we have deep borehole disposal concepts, which could be at various depths. They could be for various different types of waste. And they're obviously quite different to a deep geological repository, which is a large mine structure. These are relatively small diameter and so restricted in what they can hold, but they've got considerable attractions, as I hope you'll hear. We'll also be hearing a little bit about shallower borehole disposal, particularly for disused radiation sources. And we'll be looking at some designs of deep borehole disposal which are not vertical, which are deviated. So they go down vertically and then move out sideways. And one of the attractions of deeper disposal is that it provides increasing isolation of the waste and decreasing water flux and so on as you get into greater depth. And it also becomes more technologically challenging, as we'll hear. So that's the kind of thing we're going to be discussing. You can see on the scale at the side, we'll be talking about depths from a few hundred meters down to maybe 5,000 meters. Today and tomorrow, we're going to look at the potential and some of the issues that are associated with these solutions. The workshop's going to be split into 2 sessions. If you could show the next slide, please. The next slide. Today, we've got quite a busy day. We've got 5 presentations, and we're going to have a panel discussion at the end. Our panel today, and I'm going to ask them in a few moments to introduce themselves, are going to be looking at both strategic aspects and opportunities of deep borehole disposal and some of the technical issues behind them. And tomorrow, the panel will be extended with a further group of experts to look at some of the current, recent and upcoming technical projects which are aimed at evaluating and developing deep borehole disposal further. So going back to the previous slide for today, we're going to be hearing from Philippe Van Marcke from the IAEA on disposal concepts for small inventories. I'll then be talking about which programs might find most use from borehole disposal. And then we'll have Pat Brady and Jeff Fries from Sandia National Laboratories talking about the large amount of work that they've carried out over many areas, safety assessment, design work, costing, and so on. Then we'll have a presentation from University of Sheffield from Carl Travis and Fergus Gibb. That's going to focus on a lot of technical issues, but particularly on sealing of boreholes. And the final presentation today is going to be from Vladimir Lebedev, who's going to be talking about the safety case concept that's been developed within the NEA. And we're going to be asking the question, can you apply it to deep borehole disposal as well as other types of deep geological disposal? So just before I move on to ask the panel to introduce themselves, just a reminder, if you've got questions or comments, please answer them or pose them by pressing that Q&A button on the bottom of your screens. We're not going to be answering them directly today, but the panel is going to answer them in groups in writing after the webinar, and we'll be posting their written answers up on the IFNEC website along with the recording of the talks and of the panel sessions itself. There will be questions in the discussion sessions at the end of each day. I've got a group of general questions which I'm going to be posing to the panel, and I hope they're broad enough to cover a lot of the issues that you might, as an audience, be thinking of asking yourselves. So, to today's panel, if we could go over to the gallery view, I'll ask each of the presenters briefly to introduce themselves, and I'll begin with Philippe Van Marcke, please.
Okay, thank you, Neil, and good afternoon or good morning or evening to everyone. I'm Philippe Van Marcke. I work for the IAEA since 2015, supporting member states with their plans for the disposal of radioactive waste. And before joining the IAEA, I was involved in the Belgian R&D program on geological disposal.
Thank you, Philippe. Patrick?
Good morning. I'm Patrick Brady. I'm a senior scientist at Sandia National Laboratories. I'm part of the large team of folks working on deep boreholes. Before that, I worked particularly working on geochemistry and radioactive waste disposal at Yucca Mountain and at the WIPP site in Carlsbad, New Mexico.
Thanks, Patrick. And also from Sandia, Jeff Fries.
Yes, hello, I'm Jeff Fries. I'm a manager at Sandia Laboratories. I used to be a flow and transport modeler. I spent time working on the WIPP project, a mine repository, the Yucca Mountain project, another mine geologic repository. And since 2009, together with Pat and several others at Sandia, we've been quite heavily involved in deep borehole disposal R&D. Thank you.
Thank you, Jeff. Over to Sheffield now, and Carl.
Good afternoon. My name is Carl Travis. I'm a reader in computational physics and nuclear waste disposal. And that's the same as associate professor in the USA. My background is in chemistry and chemical physics, and I joined the Sheffield Deep Borehole research team in 2003. And since that day, I've been working with Fergus and the wider members of the team on various issues to do with deep borehole research, many of which will be covered in today's talk.
Thank you, Carl. And Fergus? I think Fergus is muted. Okay, we'll get back to you on the panel session at the end, Fergus. No escape. Vladimir, could you introduce yourself, please?
Thank you. Good afternoon, everybody. I'm Vladimir Lebedev. I'm the Deputy Head of Division of Radioactive Waste and Management and Decommissioning of the NEA, OECD NEA. And my main background is management of radioactive waste. Before joining the NEA, it is my second job within the NEA. My first job finished at the end of 19th. Before 7 years, I have been working for the NEA in the same division as administrator of waste management. Before, I worked in a state corporation, Rosatom, in the Russian Federation, and also I have worked in enterprise on waste management in the area of treatment of waste with methods of inductive melting. Thank you.
Thank you very much, Vladimir. Okay, we'll start to move on to the presentations now. We're
back, Neil, if you want.
Just a reminder. Oh, Fergus, there you are. Could you introduce yourself, please?
Yeah, sorry about that. I'm Fergus Gibb. I'm Emeritus Professor of Petrology and Geochemistry in the Department of Materials Science and Engineering at the University of Sheffield. My background, like Neil's, is in geology, and I became interested in the disposal of radioactive waste back in the 1980s. I have been researching and publishing on deep borehole disposal for almost 30 years, including since 2009 collaboration with our friends at Sandia National Labs. I've appeared as an expert witness before several national government bodies and served 5 years on the UK government's Advisory Committee on Radioactive Waste Management.
Thank you very much, Fergus. Well, we'll now move on to the first of the presentations. Just a reminder to my fellow panelists that at the end of each of these presentations, if you've got any comments to make or any questions to the speaker, please do ask them. Don't save them all until the final panel discussion. Okay, over to you, Philippe.
Okay, thanks again, Neil. Next slide, please. So I'm gonna talk to you about an upcoming IAEA publication that is titled Underground Disposal Concepts for Small Inventories of Intermediate Level and High Level Radioactive Waste. So this report is now in the final editing stages, and I expect that it will be published in the next few weeks or months. So what is this report about? Well, we started the work based on the observations that member states, IAEA member states, with a small inventory of radioactive waste can find it challenging to develop a safe, effective, and economically feasible disposal solution for their inventory. And with this report, we want to present some sort of a portfolio of disposal concepts that these member states can consider as a disposal solution for that small inventory of waste they have. So it's only about intermediate level and high level waste, not about low level waste. Next slide, please. So to explain that, why that is, let's first have a look what these waste classes mean. So the IAEA waste classification scheme classifies radioactive waste based on the disposal requirements that apply to them. So if you have very low or low level waste, these you can safely dispose of near the surface. But if you have intermediate level waste because of its content, and particularly because of the content of long-lived radionuclides, these wastes require a higher degree of containment and isolation than you can achieve near the surface. So that's why these wastes need to be disposed of underground, usually at depths of tens to a few hundred meters. And then finally, you have high-level waste, and these need to be disposed of in a stable geological formation several hundred meters below the surface. So basically, if you have that small inventory of intermediate level and high level waste, you will need to look for a disposal solution underground. Next slide, please. So that on itself is not a problem. Worldwide concepts for underground disposal of these waste have been developed and even implemented. You can see here a couple of examples from Sweden, USA, and France. So these concepts all foresee in the construction of a mined repository several hundred meters deep. So respectively in crystalline rock, in salt, and in clay for these examples. So these concepts were developed for significant waste inventories, but if you only have a very small amount of radioactive waste that needs to go underground, it can become economically very challenging because of the high 1 million waste drums. You still need to construct these access shafts or access ramps, and they usually are very costly. So that's why this problem of affordability for a small inventory, so to speak, mainly manifests itself for these waste and not so much for surface disposal of low-level waste. And that's why our report is focused on underground disposal solutions. Next slide, please. So what are these disposal solutions that we presented in the report? A first option is disposal in an underground silo several tens of meters deep. And this is what ARAU, the Slovenian waste management organization, plans to do for the disposal of their low-level and short-lived intermediate-level waste. So they plan first to put their waste drums in these concrete containers you can see on the left, and these containers then go into that disposal silo, and that silo will have a depth of 55 meters and a diameter of 27 meters. Next slide, please. Second option presented in the report is that you use underground caverns, again at depths of several tens of meters. The example here is the underground facility that Fortum in Finland operates. So at the Loviisa site, the site where they have their nuclear power plants, they constructed these caverns you can see on the slide at the depth of 110 meters, and that's where they put the operational waste and in future also the decommissioning waste of their nuclear power plant. Next slide. Third option is borehole disposal, and Neil already mentioned it. This concept is developed for the borehole disposal of disused radioactive sources. The Malaysian Nuclear Agency is currently in the process of implementing this. So they have received a license application for this concept in July 2019, and in the very near future, we should see this concept being implemented, being realized in Malaysia. So they have an inventory of 13,000 disused radioactive sources, relatively small activity, a total activity of 1 terabecquerel. These sources are also very small, so that total amount of sources will be put in a total of about 55 of these stainless steel disposal containers you can see at the center of the slide. And these disposal containers will then be put in a borehole. The borehole will have a diameter of about 20 centimeters and a depth of 175 meters. Next slide, please. A fourth option is that you use existing underground infrastructure and you convert it into a disposal facility. Example given here is the Morsleben facility in Germany. So this is an old potassium mine that in the 70s they converted into a disposal facility for low and intermediate level waste, predominantly short-lived intermediate level waste. They did that until the end of the 1990s. and BGE, the operator of the facility, is now in the process of closing that facility. And then next slide, please. The final option included in the report is very deep borehole disposal, and we defined in the report very deep as kilometers deep. Now, this concept has not been implemented up to today, but several organizations looked into it and have examined it, among which Sandia and Pat Brady and Jeff Fries will talk later in this webinar about their work on this particular concept. Next slide, please. Now, I understood that this webinar, mainly the focus is on high-level waste disposal. So what are the options if you have a high-level waste, including spent fuel inventory? Well, the waste classification scheme tells us that these wastes need to be put in an underground facility several hundred meters deep. So that leaves you with these options. And that's the first takeaway message I'd like to convey, is that if you have a very small inventory of high-level waste or spent fuel, and you see that, okay, the concepts as developed by the USA, Sweden, France, etc., you see that these concepts stretch the financial capabilities, the resources you've put aside for your disposal facility. You may want to, or you may wonder, are there any alternatives for these mined repositories? Well, in that case, you may want to look into the option of borehole disposal or the use of existing underground infrastructure and convert it into a disposal facility. Next slide, please. So let's first have a look at that latter option, converting existing infrastructure. I think the advantage is obvious. If infrastructure is already there, so you could say, okay, maybe that will be a cost saver, that it's already there. You might also have a lot of data available at the site, which could reduce your site characterization efforts. However, it's important to emphasize a few messages of caution about this option. First of all, refurbishing and converting a mine or underground infrastructure, that on itself can be very costly, and it might already outweigh the cost saving you had in mind by using that existing infrastructure. Secondly, you may need to backfill a lot of that infrastructure, and that may be an incredibly significant task and could be very costly. The picture here is again the Morsleben facility I showed a couple of slides ago. BGE is in the process of backfilling some of these galleries, and the estimated cost for these operations was around 2 billion euros. And so that itself could already be a big cost driver as well. Furthermore, your mining activities could have disturbed your host rock. You may find yourself in a very complex geology with complex geometrical structures. So that might make it also difficult to, in some cases, to develop a solid and convincing safety case. And finally, the very fact that you have a mine there means that there's something of value in the underground, and that could increase the probability of a human intrusion scenario. Next slide, please. Let's then look at borehole disposal. And I already talked about two possible concepts or two types of borehole disposal facilities. The first one is borehole disposal for disused radioactive sources. That was at depths of several hundred meters. And the other one was very deep borehole disposal, kilometers deep. Now, this is the other main takeaway message I'd like to give is, do not think of these two concepts as two variants of the same thing. Neil already touched on it in his first slide, but the safety concept underpinning these two concepts you see here are in fact fundamentally different. In the disused you place the waste in an environment that's hydrogeologically connected to the biosphere. If you go kilometers deep, you can find environments there that are hydrogeologically isolated from the biosphere. So I'm not saying that that's always the case, but you can find environments where the groundwater does not communicate with the surface. And the safety assessment and the safety case for such a situation are very different. So maybe we'll have the opportunity to talk a bit more about that during this webinar, but keep in mind, when you see these variants and differences in depths, sometimes there's much more to it than only the geometrical difference, that the one is a bit deeper than the other. Next slide, please. So if you look at the advantages of the borehole disposal concept for sources, the pros are that the borehole construction can be done relatively cheap and in a short time. So the borehole that they will drill in Malaysia, the order of magnitude of the cost is in the hundred thousands of US dollars, and it can be drilled in a month's time, including mobilization of your drilling equipment. Secondly, I mentioned it has a diameter of only 20 centimeters, which means that it has a very small footprint, which provides the high degree of isolation. The IAEA has also published a report presenting several generic post-closure safety assessments of this concept. And these assessments show that the concept can be implemented safely in a wide range of possible sites, geospheres, climate types, etc. And finally, the concept is a very well studied one, and soon it will be implemented in Malaysia. Constraints or disadvantages? Well, obviously the borehole diameter constrains what you can put in the borehole. It also constrains the engineered barrier that you can design around your waste. And secondly, this concept has not been studied for the disposal of high-level waste or spent fuel. Should you want to explore the suitability of borehole disposal at these relatively limited depths, it will require that you evaluate the combination of having a potential direct pathway between your waste and the biosphere, formed by the borehole itself, and the fact that it's heat-emitting waste, and that heat will create an upward hydraulic gradient or may create an upward hydraulic gradient. So demonstrating that that combination of these two factors will not pose a problem, that can become challenging. Next slide, please. So borehole disposal, very deep borehole disposal. Again, in the report, we define that as borehole disposal in an environment that is hydrogeologically isolated from the biosphere. So if you can demonstrate that, that's the case, and if you also can demonstrate that these conditions will prevail over the time frame of your safety assessment, then your concept has the potential to provide a high degree of containment and isolation, even for the highest activity and the most problematic waste stream. It may also be, because of the difference in the safety concept, that the scope for your site characterization work for this particular concept may be more limited than the site characterization you need to do at depths that are hydrogeologically connected to the biosphere. So depths of mined repositories or boreholes several hundreds of meters deep. The constraints, it's the same. The borehole diameter constrains the size of your waste packages. And secondly, I mentioned it already, no one has yet implemented it or even developed a license application for this concept. So there's a lack of that practical experience. It may also make it a little bit more difficult maybe to find public acceptance for this concept if it hasn't been implemented anywhere else. Next slide, please. I just want to then take the opportunity to inform you that in 2019, we launched an IAEA coordinated research project on the borehole disposal of radioactive waste. So a coordinated research project means that the IAEA brings together several organizations that work together on a particular topic. And in this case, that is then the borehole disposal of radioactive waste. We have 15 participating organizations that you can see here. There are from 11 different member states. And it's also worth mentioning that we have both regulatory bodies and implementing organizations represented in the CRP. Next slide. And then my final slide is just to inform you that there's also an IAEA safety guide specifically to the borehole disposal of radioactive waste. It was published in 2011, and currently the IAEA is in the process of updating this safety guide. Next slide, please. So that's the end of my presentation. Thank you for attending it. And of course, if you have any questions, feel free to ask.
Thank you very much indeed, Philippe. It's impressive, I think, from your example of Malaysia, that it's able to put all of one category of its waste into a single borehole. And I think that's something we'll be looking at later on in the presentations this afternoon as to exactly what you might use these boreholes for. What's a question to you, Philippe? The coordinated research program you mentioned, what's the sort of balance of interest between shallower boreholes and deep borehole disposal in the group that you for this?
Yeah, thank you for that question, Neil. So one chunk of the CRP focuses on further working on borehole disposal of disused radioactive sources. So a few member states Bulgaria, South Africa, Indonesia, and Brazil are particularly interested in that concept. But there are also some other participants from Norway, Canada, Australia, and they are more interested. They're not interested in borehole disposal of dissociated radioactive sources, but they want to explore if the concept can be also used for other radioactive waste than dissociated radioactive sources. So there's a bit of a 50-50 balance, let's say, between countries really focusing on source inventories and other participants have an interest in other radioactive waste and sources.
Yeah, that's great. It's encouraging to see this moving ahead, I think. In fact, one of the things we can look at tomorrow is where things are going to in the future and what kind of projects might be coming up and what opportunities there are for collaboration. Any questions or comments from other members of the panel at this point?
Philippe, could you state once again when you expect the report to be coming out?
It's a matter of, I think, a couple of months maximum. So the report technically is completely developed. And now it's a matter of putting it in the right format, doing some final editing. Yeah, I think, again, and then the report can be published. I think if we're very lucky, end of this year, it takes a little longer at the beginning of next year.
Right. Okay, thank you very much indeed, Philippe. We'll move on, I think, to the next presentation, which just happens to be me. And I'm going to be talking a little bit about some work I did last year, which was to try and evaluate who deep borehole disposal might be most useful for, what type of program, what type of national radioactive waste management program might find deep borehole disposal of most benefit. So I'm going to talk a little bit about the history of deep borehole disposal, just a few words on that, and then I'm going to look at some of the drivers that would point you towards deep disposal, or might say that they are not suitable for certain types of your waste. So if I could have the first slide, please, the next slide. As Thomas said right at the beginning, there's high levels of intrinsic containment and isolation are possible once we go down to depths of some kilometers for borehole disposal, which obviously makes it a very attractive proposition. And it's, I guess, slightly surprising that there's been relatively limited progress in deep borehole disposal beyond the conceptual stage up to this point. Over perhaps the last 20 years, there's been relatively little progress. Most of the progress that's taken place has been within the last 5 to 10 years or so. I would say there's really been a new surge in interest and activity, and it's actually building up speed now. So we're actually going to be seeing a lot more interest on borehole disposal over the coming years. So we've got the IAEA program that Philippe talked about. We have the deep isolation work, which we'll be hearing about from Chris Parker tomorrow. So I'd urge you to come along for that. And the potential field trial that's been considered in Australia, which again we'll be talking about tomorrow. But first, in my talk, a bit of history, and then some conclusions that I'm going to draw on what type of waste management program might find deep borehole most useful. So the next slide, please. Just kicking off, really, I found this text from a report that was written 63 years ago. This was the US National Academy of Sciences was the very first group to look at geological disposal for radioactive waste. The question had been posed, what should we do with our long-lived radioactive waste? Back in 1956, 57, and the Academy panel came together to consider this, and it included some of the great names of geosciences at the time, and two of them are shown here. Harry Hess, who is known as the father of plate tectonics, on the left there, and Marion King Hubbard, who's known as the Oracle of Oil, and was the generator of the concept of peak oil. And they were both members of this panel, and this is a transcript of one of the discussions they had. Somebody had asked them how deep should they go to achieve isolation and containment, remembering that this was the very first thinking that was being done about deep geological disposal. It's rather amusing to read what they said. It's a verbatim transcript, including the laughter at the end of the second comment about deep meaning as deep as possible. But it is very interesting to see that their conclusion at the time was they were looking at something between 300 meters and 3 kilometers were the sort of figures, or maybe even deeper. So even back 60 odd years ago, people were thinking within the same depth range of what we're talking about for deep geological repositories and deep borehole disposal today. Next slide. Well, that early work led on to some more detailed studies. 45 years ago, in 1976, there was a report carried out by Battelle Laboratories for ERDA in the USA. They looked at very, very deep boreholes. They looked at 10 to 20 kilometers super deep boreholes, but they concluded that the engineering was doubtful and the concept really wasn't viable. However, a matrix of deep boreholes down to maybe 2 kilometers looked more promising. They thought it had enough merit for a feasibility study, even though they thought there were formidable problems to do with sealing and disposal of the mud. They were thinking of drilling, conventional drilling technologies, obviously, at that time. A few years later, ONWI, also in the USA, looked at this again, and they, by that time, had concluded that deep borehole disposal was credible, and the reference system is technically feasible, logical, practical, and achievable by the year 2000. So they were looking 20 years into the future. And it's interesting to think that really after that, not a great deal happened. If you go on to the next slide, please, next slide. About 20 years later, Fergus and I looked at this and said, well, what's really happening on deep borehole disposal now? There's not been much activity at all. All of the development work has been on conventional geological repositories. So we revisited it, and our conclusion was that it really was a very final waste management solution. It was very appropriate for things like fissile materials, which you might want to dispose of to make them practically irrecoverable. It's truly final because you could make the wastes totally irretrievable. And it would also be suitable for programs with small waste arisings. That was one of the other conclusions we came up with. But we also concluded that if you couldn't really communicate the greater isolation that you get with deep borehole disposal, then the lack of retrievability might be a problem. And that's going to be an issue we come back to in the discussion sessions. Do we want to design these for retrieval or not for retrieval? Next slide, please. Well, over the years after that, there was a lot of work started to be generated, in particular by Sandia Labs. My colleagues at Sheffield were doing a lot of work. We'll be hearing about both of these later on. Next slide. This was you've seen this slide already. You'll be seeing it again later on. This was the concept that emerged from the Sandia studies. It's worth just pointing out to our audience that again, that these studies of deep borehole disposal are looking at disposal at considerable depth, 3 to 5 kilometers, and all of the rest of the borehole above that is sealing. It's to isolate the waste and to contain the waste. So evaluating, studying, and developing the kind of sealing that might be needed is a critical part of the concept, and you'll be hearing about that again today. Next. Okay, now to the main part of what I'm going to talk about. Because the volume of deep boreholes is limited and the diameter is limited, it really limits what you can put down them. So let's have a look at what technically you might, what kinds of waste technically deep borehole might be suitable for. It's obviously attractive for wastes with high concentrations of long-lived radionuclides. They motivate a solution that guarantees a very high degree of isolation for a very long period of time, which is exactly what you get with deep borehole disposal. So you're only really looking at the highest activity waste. And you might, amongst those, find even some lower, shorter-lived wastes that have got very high specific activity, for which you've got very small volumes, and you need to find a special solution. And this has been looked at in the USA for cesium capsules from Hanford, for example. And that could be a particular application, a particular type of waste. It's undoubtedly important that the waste you're looking at have a relatively small total volume. The volume of a borehole, a deep borehole, the usable part of it is at most a few hundreds of cubic meters. So you're really looking at wastes that have only got volumes of a few tens to a few hundred cubic meters in your national inventory. If you've got thousands of cubic meters, you'd require rather a lot of boreholes to put them down. It makes it look less attractive. And because the diameter of the borehole is limited, you're limited to small package sizes. So 400 to 500 millimeters is as much as you're likely to be able to get down a very deep borehole. Obviously, in shallower depths, you can get bigger packages, as we'll see. And as I mentioned earlier, we concluded that this solution might actually be very attractive for separated fissile materials. For example, some countries are building up plutonium stocks, which are not likely to be reused as an energy source, or may well not be reused as an energy source. And if it's decided that they need to be disposed of, then putting them 5 kilometers down gives an enormous nuclear safeguards protection. At the bottom of the slide here, we're seeing again the attributes that make waste types potentially unsuitable. And it's again to do with volume and package size. So those are the two limiting things that are going to make it difficult. But if you're trying to decide in your national program what you might use deep borehole disposal for, it's not just a matter of technical attributes, there's strategic issues to think about as well. And if you look at the next slide, you'll see a rehearsal here of some of those strategic considerations. And here are some reasons at the top of the slide that you might want to consider using deep borehole, either as a component of your national program, or perhaps even as something that will cater for a large part of your national inventory. There may be no other solution available for a particular waste stream. Your conventional geological facility might not be available for decades. If it ever comes along, many national programs have geological disposal programs that look very, very far into the future before anything is available. There may be time schedule demands. Early disposal of a particular waste material might be required, for example, before a geological facility becomes available. You might have no other wastes in your inventory that require geological disposal. So you don't really require a conventional geological disposal facility. That may be because you've got no other waste there in that category, or maybe you've even transferred them to another country for disposal. In some programs, you might want to use a site-specific solution for a particular category of waste. You might want to dispose of it on the site where it's stored or generated. And you might want to uncouple it from the development of your National Geological Disposal Facility. You might want similarly to remove a particular waste stream that's causing storage problems or could be problematic if it was put into the National Geological Facility. For example, if you were to put high burn-up MOX fuel in there, it's got higher heat output, prolonged heat output, makes it more difficult to build to include in a geological facility that's principally designed for other wastes. So you might want to think about putting those elsewhere. You might want to make a political statement by early disposal. You can certainly consider implementing deep borehole disposal earlier than you can conventional geological repositories. So you might be able to get on with some aspects of disposal years before you could actually implement your main geological program. And finally, the economics of deep borehole disposal is undoubtedly makes them less costly to dispose of than building a purpose-built geological facility for the same waste. We'll see some examples of costs later on. On the other hand, there are some considerations that may make waste types unsuitable for deep borehole disposal. Again, we're coming back to volumes again. Large volumes of waste in your national inventory means you're going to need a geological repository anyway. So why have a separate deep borehole facility for waste that could go to the GDF? there may be a simpler or more economical solution for the wastes that meets the disposal requirements, but still gives more spatial flexibility. And finally, you might have this requirement perhaps built into law in your country that some categories of waste have to remain retrievable after disposal, maybe for some hundreds of years. And this could make deep borehole disposal less attractive than a geological repository that you can walk into. So how do we bring all that together? If we look on the next slide, what I did was to try and look at which types of program might weld all of that information together and find it suitable. And I came up with 3 groups of countries. The first one are countries with major historic nuclear development. These are largely countries that have got into fuel cycle activities and have fuel cycle facilities, fuel fabrication, reprocessing, and so on. The drivers for those big programs, which are inevitably going to need a geological repository anyway, is that using deep borehole disposal could deal with a very specific waste stream. For example, excess fissile materials I mentioned before. And it could use that solution local to the source of the waste. So that might be one driver for them. And another driver might be a lack of progress with the geological repository, plus a need to show progress in the National Waste Management Programme. And also, if you're able to use deep borehole disposal for some of the waste, it might reduce the requirements on the geological repository. The second group of countries is the smaller nuclear power programs with maybe 1 or 2 reactors. The drivers for them is that they could use deep borehole disposal to dispose of small inventories of vitrified high-level waste, for example, or of spent fuel. And that allows them the possibility of simplifying the concept for an essential national geological facility that they'll need, for example, for their intermediate level waste. So that would allow them to relax siting and engineering requirements for the GDF, making it easier, perhaps quicker and less expensive to design and implement. And then the final group there is countries with no nuclear power, but small volumes of research waste, from reactor research waste, perhaps medical, industrial and research waste. The drivers for them are really rather similar to the previous group. If they can segregate out disposal of spent fuel, that would be good. And for some small programs, it's even feasible that all of their longer lived wastes, their higher activity medical and industrial and research waste might go into a single deep borehole. Next slide, please.
That's about 15 minutes, Neil.
Yep, I'm just about to wind up here. So one model here, which I think we'll hear more of later on, perhaps from Dirk tomorrow, is to use a borehole, different depths in a different borehole for different categories of waste. Larger volume waste in the wider parts of the borehole higher up, and the deeper parts for the more active waste. The last slide, I think. My conclusion then is that deep borehole disposal is much more likely to be a major component in the disposal strategy for smaller national inventory countries. And if you combine it with a near surface facility for some of the lower activity waste, it's even feasible that 1 or 2 deep boreholes might take all of your longer lived wastes in a smaller program. But some of the specific needs from the larger nuclear programs could really drive deep borehole disposal forward fast as well, and perhaps to greater depths. Thank you. Okay, I rather overran on my time there, but if there's any points that we can't pick up in final discussion, the panel's very welcome to chip them in now, or you can wait until the end of the session today.
Neil, I would just have a short question, really. We are talking about solid waste disposal, right? In the recent 20, 30 years, not liquid waste disposal. People sometimes mix this because we're talking about boreholes.
Yeah, I perhaps should have said that in the introduction. Everything we're talking about in this webinar is to do with solid waste disposal. In the very early days, there was consideration of liquid waste disposal at the time of the National Academy of Sciences I mentioned earlier on. And of course, there have been some trials of liquid waste disposal over the decades, but now everybody is thinking only of solid waste disposal.
Thanks. Maybe we should now move on.
Yeah. Okay. If I could move on to the next presentation and ask Pat, please, to come forward and tell us about the Sandia program.
Yes, thank you, Neil. Good morning, bonjour, dobre utra, ni hao, konnichiwa, buenos dias, morgen mitenan, and good day, mate. Can we go to the first slide? Oh, there we go. All right, what Jeff Fries and I are going to do over the next 10 minutes is describe what we have done at Sandia over the last 12 or 13 years, and more importantly, where we are going. Our goal from day one has been reducing to practice the borehole disposal. Specifically, we have tried to identify the hurdles, the technical hurdles, the regulatory hurdles, and we've tried to resolve them. Where technical gaps existed, we did the research or we funded our partners. Where there were no siting guidelines, we developed our own. Where there were no regulations, we tried to imagine what those regulations would look like. For demonstrating all of this in the field, we've worked with international partners and in the United States to see how we can demonstrate the whole process. Key to all of this is the belief that to achieve success with deep borehole disposal, we have to imagine failure. That is, we have to follow standard engineering practice and not so much look for how boreholes will achieve their objective, but what are the points where we have to pay particular attention and work out failure modes. We believe that's the key to deep borehole disposal, and hence there is an emphasis in the Sandia work on simplicity and off-the-shelf research if it's applicable. Now, we started this all back in 2009, beginning work with Mike Driscoll at MIT. And then we were fortunate enough to be able to work with Fergus Gibb and Carl Travis, University of Sheffield. This whole program that was all funded by Sandia. This whole program expanded in 2012 as the US Department of Energy began plans for doing a 5-year deep borehole field test. This was a big deal. It was roughly $100 million. Now, that you'll see some of the research that came out of that, siting guidelines and so on. That effort ended in 2016. The work that has continued at Sandia, Jeff will talk about, we've completed a number of reports, again, filling in key gaps. I would call your attention to the Harden et al. Report, which Jeff will emphasize, doing a fault tree analysis of deep borehole disposal. Again, standard engineering practice that doesn't get the attention it deserves. I would also emphasize the international collaborations have been key from the start. In particular, the one we're working with now is with the Australians. Dirk Malance will talk about a little bit of that later. Next slide, please. Let me tell you what the takeaways for Jeff and I's talk are right now. There is a lot of experience that we're going to draw on for implementation, drilling, and regulations. It comes from the oil and gas industry. It comes from the waste disposal experiences in the United States and elsewhere, and recent IAEA efforts on sealed source disposal. I would also emphasize that we focus on deep disposal primarily because it makes the safety analysis much more straightforward. I would call your attention to pre-closure operational safety assessment. This requires demonstration because this is new. How do you handle the waste at the surface? Okay. Lastly, field demonstration is critical for surface waste handling and emplacement. We'll hear more from Fergus and Carl on borehole sealing. This is not the last you'll see of it. Next slide, please. All right, if you look on the left-hand side here, there is vast international experience with deep boreholes. If you look there, what is it, about 50,000 oil wells in the United States alone going to an average depth of, that's the blue line, of approximately 2 kilometers. So the point here is that, no, we don't have an operating deep borehole right now, but we have thousands of holes that look kind of sort of like a deep borehole. If you note that the average depth, the right-hand vertical axis, these wells are getting deeper and deeper. Now, what's different between a deep borehole for nuclear waste disposal and an oil and gas well? Look on the right-hand side. First of all, the wells have to be bigger in diameter. We originally calculated 17 inches, 40 centimeters, compared to a standard oil and gas well of 8.5 inches. I'm guessing that's about 20 centimeters. But if you look down below, there's a figure from John Besick pointed out that there is institutional experience both from Russia, KTB, and Germany, and geothermal wells. The diameters we need for deep borehole disposal and the depths are achievable with existing technologies, with some modifications. The other difference is we're going into hard rock instead of soft rock for deep borehole disposal. That's where we would draw on the experiences from geothermal drilling. Third, we're emplacing waste instead of extracting oil and gas, hence the emphasis on surface handling. Four, and again, Fergus and Carl will talk in greater depth about this, there's a desire and a need for long-lasting seals. Next slide, please. All right, there are no regulations out there for deep borehole disposal, but there are regulations that we've used for decades in the United States to regulate disposal of non-radioactive waste. You look on the left-hand side of the figure, you'll see that these things go down to depths that are sort of in the ballpark for what we've been what Neil showed in his first slide. No, I think it was first, somewhere in there. These injection wells go down to a couple of kilometers. They typically put down hazardous and non-hazardous industrial waste. Sometimes it's brines. A lot of the times it's oil and gas waste. Pay attention to the bottom part there. There is to permit and regulate these wells, it's key to buttress a no migration petition. Now it requires a description of the well, the waste, and the third and fourth bullets are parameters we're quite familiar with. Basically, you have to do a transport calculation of the waste. And then you have to worry about seismicity and faults. Let's go to the right. What will be different if we took the regulations from hazardous waste injection and applied them instead to radioactive waste? Well, first of all, we have to deal with hard rock instead of soft rock. Most of our hazardous waste wells in the United States go into soft rock. A good thing for us is that our waste is solid as opposed to liquid, as Neil pointed out a few moments ago. Lastly, we want long-lasting seals. The seals don't have to last for perpetuity, though. They basically have to last long enough until a thermal pulse from the heat of, for example, spent fuel goes away. You know, for the Yucca Mountain inventory, well, that's cesium and strontium. So they have to last for a couple hundred years. I should draw your attention to the screenshot I took from the IAEA. They're looking at borehole disposal of sealed radioactive sources. And the regulatory framework for that and for the individual countries, that's also what we might use to construct an idealized regulatory regime for deep boreholes. Next slide. Oops. Oh boy, this is my last slide. Okay, this is one that Neil showed before. I'll focus on our concept, or the concept that we worked out with others. That's the deep borehole one. Note that the greater depths you have, the greater there is the reliance on natural barriers. The shallower, there's engineered barriers. I would also add that the failure analysis becomes much more straightforward as you go to the deep sense, because your failure is all in the drilling and the surface handling. If we can quantify what the risks are there, we can get much more rapidly to a safe solution. And with that, I'll hand the baton over to Jeff Fries.
All right, thanks, Pat. And next slide, please. All right, so this slide starts to address one of the questions that Neil had identified. Question number one about safety case requirements for deep borehole disposal versus a mine geologic repository. So what we have here, this figure on the right, is a list of the safety case elements. This is adapted from an NEA report for a mine geologic repository. We have, as I said, adapted it to apply to deep borehole disposal. And it turns out that it's not all that different. And this can be found in these reports. There's a fair amount of detail and description in these two reports, the Fries 2016 and Fries 2019 reports. But what I'd like to point out is there's three major categories. There's the safety strategy, there's the assessment basis, and then there's the safety assessment. So the safety strategy is the national program that's developed by the National Radioactive Waste Management Organization. And that's where you start to need to develop regulations. So for our work, we looked at US regulations for mine repositories and made some assumptions about how that might apply to borehole disposal. For the assessment basis, that's the collection of information to support both your post-closure and your pre-closure analyses, and also information that might go towards site selection. And then in the safety assessment grouping, again, you've got equally important a pre-closure analysis and a post-closure safety analysis or performance assessment. So we have taken a stab at documenting several of these things, and I'll try to summarize those on the next slides. And what I want to point out is, so this list of safety case elements, this is essentially a checklist for what you would need to establish the safety and viability of deep borehole disposal. If you're actually ultimately going to license it, you'll then be writing a license application towards some regulations, which would typically mirror a lot of these categories. So now next slide, please. So we've documented some siting guidelines, and again, this would be for a deep borehole in the area of hydrogeologic isolation. And these guidelines include technical, logistical, and socio-political factors. So the technical factors are what would help you to find a site that was deep, hydrogeologically isolated, and in competent rock. The last sub-bullet, proximity to population centers and public opinion, those are socio-political factors, and certainly for mine repositories, those are sometimes the most important factors, quite likely to be the same thing for boreholes. An important point here is these siting guidelines, it's not necessary for a site to meet all of them. The more you can meet, the more likely you are to be able to demonstrate safety, but certainly don't need to necessarily meet all of them. And again, the siting guidelines and the site evaluation needs to work together with the engineering components. If you have a shallower system, you're likely to need more robust engineered components, i.e. a waste package and seals. Next slide, please. So Pat has mentioned the deep borehole field test done over a 4-year period. We probably did R&D that was, you know, on the order of $10 or $15 million worth of research. So we did some significant work looking at drilling and characterizing deep, large diameter boreholes, looking at downhole emplacement operations, looking at seal design. Again, that was together with Carl and Fergus at the University of Sheffield. And we did some preliminary modeling of generic safety assessments, both pre-closure and post-closure. There were some potential sites identified, but the project was terminated before we actually were able to do any field work. And just to reemphasize, so the DOE is no longer investigating borehole disposal at this time. But nonetheless, we had some good accomplishments. These are listed in these reports. There's a lengthy reference list at the end of the presentation, and all of these reports are available. I'm happy to send them if asked. They're typically, you can Google search and find them. Next slide, please.
That's about 15 minutes, Jeff.
Okay, let me quickly wrap up. So Pat mentioned the pre-closure safety analysis. So this is documented in a harden report and in a freeze report listed down at the bottom. The point here is this is a fairly complicated event tree analysis. You can see there's 11 sequences that have to be analyzed. We documented the blue square sequence 7 is specifically the borehole emplacement and retrieval processes. You don't need to be able to read that. What we wanted to just demonstrate here is this is sort of typical engineering practice. And for borehole disposal, especially deep disposal, it's the operations that are likely to be the most challenging. And you know, we go with a vertical emplacement, a vertical borehole, because that's the simplest. Next slide, please. This just quickly shows the generic post-closure performance assessment. You can see this is actually 10 million years after disposal. This happened to be a high-level waste cesium and strontium capsule. So cesium-135 is the long-lived radionuclide, has a half-life of about 2 million years. And it shows that even after that period of time, cesium didn't migrate very far because it's in the area of hydrogeologic isolation. So there's no advection, there's just diffusion. And for the case of cesium, there's also sorption. So this is sort of just re-emphasizing the isolation that you get when you go deep. Next slide, please. And so in summary, just to re-emphasize the key takeaways, we've done several studies. We looked at the pre-closure operations and we identified a low probability of operational failures, but much more work needs to be done. For post-closure, we demonstrated robust waste isolation, but we feel like there's a lot of R&D that still needs to be done, specifically a field test, which would help us I guess, get better answers for the drilling and operational feasibility, deep drilling, seal characteristics, and making sure we can characterize the deep subsurface to ensure the hydrogeologic isolation. So thank you.
Thanks a lot, Jeff. You mentioned that the plans for a field test in the States are no longer with us. I mean, what developments are we likely to see from Sandia? What direction are you likely to be taking in the future? Is there a program planned out, or where are you?
Sure. Yeah. So we continue to fund the borehole work internally, and so our involvement we have a significant involvement with the Australians, with CSIRO and ANSTO, and Dirk's going to talk about that tomorrow. Our interest, we're not planning to make millions and millions of dollars implementing a borehole, but we have a great interest in this being implemented safely. And so we're happy to provide input and consult for, other operations. And the US program, it's, who knows where it's going.
You're continuing to be active here. And I think the idea of eventually internationalizing a deep borehole field test, I think is extremely attractive and maybe something we can talk about tomorrow. Anybody else have a comment or a question here for Pat or for Jeff?
I have a quick question, Neil. Can we get your slide, either from Jeff's or your original slide up? Do you know what I'm talking about? The one that shows the different approaches.
Maybe Clement can put us back to the beginning slide. That was the very first diagram.
If that's going to be a problem, my question is basically, that particular graphic shows the disposal area basically the same. Yeah, basically the same for the different depths. Is that a concept that I'm picking up correctly, or do you have potentially different disposal areas at different depths?
I guess the slide didn't. No, I think there would be different disposal areas. Again, the deep concept, the waste is at the bottom of the hole, 3 to 5 kilometers down nominally. Some of the other concepts, the waste disposal is shallower. It's maybe 1 to 2,000 meters deep. So it is different. And those numbers are not exact. I mean, they all depend on the regional geology. You might be able to find an hydrogeologically isolated competent rock at 2,000 meters in certain areas. But once you get, hundreds of meters to 1,000 meters depth, then you're much more likely to be in connection with the circulating groundwater system, which doesn't make it, impossible or wrong. It just makes it more challenging for your post-closure safety demonstration.
Thanks, Jeff. And any other points? If not, we'll move on. We're going to pick up some of these topics again, I think, in the discussion at the end of today and tomorrow, for sure. In that case, let's move on to the next presentation and move on to Carl.
Right, well, good afternoon, everyone. And I'll start by thanking the organising committee for the invitation to be on the panel and to speak today. Now, it's just been announced that the UK is to build a new PWR at Sizewell C. And this and other reactors will give rise to a wide variety of waste types requiring disposal. In our work on deep borehole disposal, on the concept, and by this I'm restricting myself to vertical holes drilled to a depth greater than 3 kilometres, we've looked to accommodate a wide range of spent fuel and high-level waste types, including these higher burn-up fuels. Can I have the next slide, please? So in this presentation, I'll be focusing on aspects of disposal that we've been researching at Sheffield, along with our collaborators, and for which we make important contributions to the safety case. And the 3 key areas I want to talk about are sealing and support matrices, consolidated disposal of spent fuel, and borehole plugs, or in other words, the final sealing. Next slide, please. So a key feature in the Sheffield deep borehole disposal concept is the use of a sealing and support matrix, or SSM as we call it. The SSM fulfills 2 important roles. Number 1, it acts as a seal or barrier preventing the ingress of saline groundwater and therefore prolonging the container life. Function number 2 is to provide mechanical support against potential buckling due to axial load stresses. At the University of Sheffield, we've developed 2 different SSMs. The first one is a low temperature cementitious grout, and the second one is a metallic high density support matrix. In this particular slide, I'm illustrating our cementitious SSM. Now, we've considered 2 options for emplacing such a seal. which we've called option 1 and option 2, as illustrated in those two schematic diagrams on the right-hand side. In the first option, the cement's emplaced following package emplacement. This is very tricky to do at depth, but Marriott Drilling, a leading UK drilling company and one of our long-time partners in researching and developing and promoting DBD, have developed a dump baler which has a potential to enable option 1 to take place. In diagram 2, or option 2, the grout will be emplaced first, and then the waste package will be gradually lowered into the cement plug, sinking under its own weight, and the action of that would squeeze the cement through the perforations in the borehole casing, filling up the annular space between the borehole wall and the casing, and between the casing and the container. Can I have the next slide, please? So developing suitable grouts or cements for DBD is extremely challenging due to the harsh conditions downhole. The grout must withstand temperatures as high as 120 degrees C and pressures of 50 megapascals, conditions which accelerate the setting of the cement. Groundwater will also have an impact on waste paste properties, especially chloride compounds, and the effects of radiation also have to be taken into account. At the University of Sheffield, we've developed a suitable grout based on a Class G oil well cement, along with silica flour, fluid loss additives, and retarding agents. We've managed to demonstrate, at least on a lab scale, that such a paste can be used in a model emplacement of options 1 and 2. And furthermore, that it shows delayed setting long enough to be delivered downhole and for a single waste package to be emplaced using coiled tubing. And that delay in setting is about 4 hours with the right composition of additives. So the function of the retarding agent is only to delay setting, and once the sealing and support matrix is set, the additives fulfilled its function and is degraded, so it doesn't matter what becomes of it due to any irradiation. I'll have the next slide, please. So our second type of SSM, I mentioned 2, is a dense lead-based low melting point alloy in the form of a fine shot. And we term this the high density support matrix, or HDSM for short. Can we play the movie, please? So this short video shows a lab scale mock-up of how HDSM might be emplaced by coiled tubing. So we've got a large acrylic tube, and inside another acrylic tube of shorter diameter with perforations, and then right in the center we've got a steel cylinder, and then we're pouring lead shot down a tube through the water-filled tubes, just to show that it does indeed go through the perforations of the borehole casing, fills the annular gap quite nicely, leaving no major voids. I'll just let that play a little bit more. So the shot would sink through the borehole fluid and enter the annulus via the perforations. And then radiogenic heat from the emplaced waste containers will melt the HDSM within weeks of its emplacement. And that allows a dense metallic liquid to form, which will then fill any smaller gaps, nooks and crannies and crevices. Not only that, if it's engineered properly, it will provide a slightly neutrally buoyant environment for the nuclear waste containers, which helps if we're disposing of something like spent fuel with very dense waste container packages. So after a few decades then, once the thermal pulse has abated, the molten liquid metal will cool and solidify and effectively solder the waste containers into the borehole. And again, going back to the borehole, the dump baler technology I mentioned that Marriott Drilling have developed, if we were to employ that technology to emplace HDSM, you could deliver a more precise amount, avoiding any waste. So HDSM is easier to emplace, more tolerant of borehole conditions than a cement, and it would be our preferred choice over and above a cement. But it's nice to have a backup for those cases where insufficient heat is generated from the waste to melt the HDSM. We'll have the next slide, please. Now, with the annulus filled up with a sealing and support matrix, that, you hope, eliminates any vertical transport of radionuclides by advection. However, it's been suggested that a possible alternative pathway in which radionuclides could reach the biosphere is by advective transport through brine-saturated host rock. So we've modelled that situation just to get an estimate of how long it would take for a particle, a hypothetical particle, to be transported up to the biosphere by this mechanism. And the model we've used, the cesium and strontium capsules from Hanford. We've assumed we've been able to dispose of the entire Hanford inventory of those capsules in a single borehole for the purpose of the calculation. And what we find is that a particle will travel only 100 meters in 1 million years. I'll have the next slide, please. I'll now talk about the second topic, which is consolidated disposal of spent fuel. It's a somewhat controversial topic, mainly because consolidated disposal potentially exposes workers to more irradiation. But there are other there are advantages to it, and I'm sure those disadvantages could be overcome. So the idea here is you can get a very efficient disposal if you take the fuel rods out of the reactor and you pack them inside a cylinder. It could be a stainless steel container, attempting to get a higher volume ratio as you can, and then you would slowly heat the package up. That's the container with its fuel rods, to drive off any residual water or moisture that might be in existence there, and then you fill the gaps in between the fuel rods with molten lead or perhaps molten glass, and then you will cool it down gradually. You'd have to do that to avoid any cracking, and then you weld on the lid and decontaminate. So that's how you prepare a consolidated container for waste disposal. The diagram on the left-hand side shows a typical AP1000 fuel rod with a length of 4.58 meters. So these rods, to dispose of them in this particular way, would require a 5-meter waste container. And that would be very dense, and hence the HDSM would be advantageous with its neutral buoyancy environment that it will provide. So consolidation enables the diameter of the waste package to be tailored to the most economic size consistent with borehole costs. The diagram on the right is just an illustration of how we've treated the source term in the subsequent modelling work. The decay heats, the graph on the bottom right, show various waste types. MOX at 65 gigawatt day per tonne burn up, for example, MOX at 55 gigawatt day per tonne burn up. And so that FISBIN data has been used to create the source term along with a thermal resistance model. I'll have the next slide, please. So this plot is a result from a typical modeling simulation, a modeling run to determine the temperature pulse. And the 3 different colored curves represent the temperature that would be achieved on an axis line along the middle of the container, of the single waste container, along the bottom and along the top. And the container has 1,000 pins of 15-year-old uranium fuel with a 65 gigawatt day per tonne burn up. The 2 horizontal lines, 185 and 192, represent the solidus and liquidus for the high density support matrix. So the aim of the game is to make sure that the temperature exceeds the solidus. And we can see from this data that it does, apart from at the top of the container. That's not such a bad problem, because when you put the next container in, heat from the container above will raise the temperature at the top of the container below. And even if it doesn't, one can always put either more pins in, a different makeup of waste. There's many different variables one can play with to achieve that aim. So the point is that modeling allows us to explore a wide variety, a wide parameter envelope quite quickly. I'll have the next slide, please. So this chart, I've called it a selection chart, this SSM selection chart, summarizes a vast number of modeling results, although I've only shown a few on this particular, simplified the picture somewhat. The different coloured bands demarcate regions where each of the different two types of SSM are applicable, depending on combinations of number of fuel pins per container and post-reactor age of the fuel. So you can see at the bottom, if a pair of those two variables lies in the brown region, we'd advocate using our special cement that we've developed. Whereas at the top, in region A, the green region, if a pair of variables, if we plot a parameter, a coordinate in that zone, we'd be able to comfortably use the HTSM. And the numbers on the symbols represent the days it takes to melt the HTSM, or to begin the melting of the HTSM. Okay, so modeling is very, very useful for achieving these scoping studies. Let's take the next slide, please.
Coming up on 15 minutes, Carl.
Yeah, I'll move a little bit more quickly. So the real outstanding challenge to implementing DBD is not so much drilling a hole to the given depth, although that is a challenge in itself, but of final sealing of the hole, or plugging and abandonment, as it's called in the oil and gas industry. And of the many sealing materials, none have been demonstrated to last for the thousands of years necessary for a post-closure safety case. One significant safety factor, though, in vertical DBD into basement rock is the presence of density stratified brines, which acts as a natural seal preventing advection. Now, the construction of a borehole disturbs that natural salinity gradient, but once the hole's been filled and sealed, that salinity gradient will re-establish itself over the course of time. So as Pat said, the seals only need to last as long as the time it takes for that restoration process to occur. So it's an important parameter to determine how long does it take for that restoration process to occur. And modelling is a very powerful tool to answer that question. The two plots I'm showing here shows the difference in pressure with depth for a column of fresh water and a column of brine, data taken from the Urak 3 geothermal hole in Germany. The plot on the right is the difference of those two curves, and you can see it's approximately a quadratic pressure difference. And using that quadratic pressure difference as a boundary condition, I'll have the next slide, please, we're able to do some modelling of how long this recharge time takes. So this plot here shows the result of a model. It's one I showed at the waste management meeting in Arizona earlier this year. On the left-hand axis, we're plotting total dissolved solids, and on the bottom, depth. And each of the different coloured curves is a different interval of time, and they're all increasing the direction of the arrow. And we can see that from this, a tenth of a year, a little over a month, we've started to almost build back up to the equilibrium salinity gradient. So we're not talking a very long time for these things to, the salinity gradient to establish itself. Now, engineering solutions exist for reducing the scale of groundwater perturbation. If we wanted with different permeabilities, that number of years is likely to increase. But as I say, engineering solutions exist to reduce that recovery time. We'll have the next slide, please.
Running just a little bit long, Carl.
Yeah, so notwithstanding the length of time traditional seals need to last, for example, cements, clays and concretes, one of the major problems with these seals is they don't seal the disturbed rock zone. And this is the little red hashing there on the diagram shows cracks and fissures in the rock created by the drilling process. That can act as a shortcut pathway for transport to the biosphere. Next slide, please. So at the University of Sheffield, we've developed a concept which gets around this problem, and we call it rock welding. The idea is that you fill the top of the disposal zone with crushed rock and some traditional seals and a cement plug. More crushed rock, you put down a down-the-hole heater, supply some current from the surface. The current will, or power will heat the rock, surrounding rock, the crushed rock, and form a molten, or start to melt the saturated crushed rock. And that will melt even the rock a few centimeters or more into the host rock, closing closing the cracks in the disturbed rock zone. And you can make multiple welds in the borehole. We'll have the next slide, please. And this slide simply shows some modeling work we've done for a hollow heater design. I'm just showing how temperature varies with time along different points along the top and the middle at different points in the heater and in the host rock. Just so that we can see, if we'll have the next slide, please, we're able to produce a chart like this, which tells us anything within the red line is in the weld zone. It gives us the spatial extent of the weld zone and allows us to see whether we need to supply more power from the heater or change the physical dimensions of the heater to achieve the ends that we want. This is all done by modeling work. I'll have the final slide, please. So to summarize then, disposal in deep, greater than 3 kilometer vertical boreholes rely principally on an appropriate geological barrier, including density stratified groundwaters, appears to be a safe and versatile concept for vitrified waste, spent fuel, and other types of high heat generating waste. Further research is underway at the University of Sheffield to design improved seals, emplacement methods and plugs, mostly modelling, but a field test is now required for validation and refinement. Final point, its potential economic, environmental and technical benefits, including proof against future events such as earthquakes, climate change and glaciations, must make it worthy of serious consideration by governments and waste management organisations. Thank you. If we just put up the acknowledgement slide. Thank you. So I just want to acknowledge these people, funding bodies and collaborators. Thank you.
Thank you very much indeed, Carl. You've raised a lot of interesting points there. There's obviously a lot of potential solutions to some of the issues that are raised about deep borehole disposal, and obviously in particular the sealing issue. How do you get packages in and things like that? And in particular, how do you seal them and isolate the waste deep down the borehole? We're running a wee bit behind time, so I hope you don't mind if we put those, we're going to be talking about sealing later on and certainly tomorrow. What I'd like to do is move on to the last presentation to give us a little bit of time for the panel. We'll pick up questions and comments on that later on. So Vladimir, could I ask you to tell us about safety case and how the safety case for deep geological repositories might be adapted for deep borehole disposal?
Thank you, Mr. Chair. Good afternoon. And I'm representing the NEA, particularly the NEA Radioactive Waste Management Committee, and its work in the area of safety case for deep geological repository, and I'm going to share some ideas how the committee can proceed with its development, taking in account this concept, concept of deep borehole disposal. Next slide, please. The NEA consists of 8 standing technical committees which cover different aspects of nuclear energy, and the Committee on Radioactive Waste Management is the committee which works in the area of management of radioactive waste, and particularly in the area of development of safety case for deep geological repository. This activity, this mission of the committee is part of assistance of the NEA to member countries in order to support the sustainable, safe and economically efficient development of the national nuclear programs. Next slide, please. The NEA and RWMC considers the safety case as an instrumental for demonstrating long-term safety of the geological repository. As this concept was internationally accepted, I would just mention that the IAEA in its safety standards states that safety case shall demonstrate the level of protection of people and the environment provided and shall provide assurance to the regulatory body and other interested parties that safety requirements will be met. What is important that safety requirements are universal for all types of disposal facilities. And deep boreholes is not exclusion of this requirement. Main requirement is that safety case should demonstrate the safety of disposal solution. Next slide, please. The safety case is identified as a formal compilation of evidence, analysis, and arguments that quantify and substantiate a claim that disposal will be safe. It should demonstrate the possible evolution and performance of the chosen site, host rock, engineering system, and demonstrate that it would be safe. It is bounded with the confidence. The safety case, it is tool of support the decision making, and also it helps to review the project status, to test methods of safety assessment, or sometimes it could be used for prioritization of research and development activities. For the moment, there is no any universal format of the safety case, and safety case can differ in details, but key elements, they are accepted worldwide and they are next. A statement of purpose and context, safety strategy, which covers siting and design, management and assessment strategy, basis for assessment consisting of concept, information and understanding, models, methods, and so on, and safety assessment itself, which operate with evidence, analysis, and arguments, and final stage of the safety case development and synthesis, which visualize all previous safety assessment in the set of key findings and statement of confidence. Here you see the NA safety case brochure, where the safety case is described in detail, but I would add here one more brochure, NEA 2013, which describes the safety case for deep geological repositories in post-closure period. Next slide, please. Within the RWMC, the safety case concept is elaborated since 1989, and the committee was focused on safety case for the deep geological repository. Safety case for other types of disposal facility was not a subject of its activities for the moment. The process has started in 1989. It was discussed within the NEA symposium, and first consolidation of the state of the art in safety assessment methods was reached. NEA RWMC created expert group on integrated performance assessment, IPAG, which in 1994 developed the safety case concept, which was consequently adopted by national programs and internationally, and introduced into safety standards of the IAEA and the EC. From 2000, the NEA created integration group of the for the safety case, IGSC, which works under the Radioactive Waste Management Committee, and develops the scientific basis, strategies and tools for the safety case for deep geological repository. And not only this group is focuses on the deep geological repository issues, on safety case. Many other NEA groups involved in this process and contribute to the holistic joint understanding of the nature and of the development of the safety case. In 2018, the RWMC adopted the holistic approach for planning of its strategic development, and as part of this holistic approach, the RWMC decided to extend the scope of work in the safety case development area, and in order to cover all types of disposal facilities, not limited to deep geological repository, but near surface facilities, other types of facilities, middle depth facilities, and deep borehole disposal, may be a part of this consideration. Safety case for other types of facilities to be considered based on the gathered experience and knowledge about the safety case for deep geological repository. And the IGSC is supposed to lead the discussion, and other RNA groups like Forum on Stakeholders Confidence, Group on Regulatory and Implementary Dialogue, and others to be involved in this wide discussion of the process. And this year, the NAA planned to hold workshop on safety case for all types of disposal facilities, but due to the current situation with COVID, it was postponed to now. The date is end of June next year in Romania. We are still supposed to have it in not in online but in physical form, and this workshop is going to discuss and identify directions of future RWMC development in the areas of safety case. And deep borehole disposal concept can be discussed within this workshop. At least I collected inputs for that here, and will inform the program committee in order to include at least this item within the discussion in the program. Next slide, please. As I told, the RWMC accepted the holistic approach for planning of its future activities. And as you see, the safety case, it's oval in the middle. It is not just activity of one group. It is under the general guidance of the Radioactive Waste Management Committee. There is a working party, IGSC, which has subgroups oriented on study of features of potential host rocks like salt club, clay club, and crystalline club, and they contribute with scientific and technical input to the safety case development. At the same time, we have regulators forum and group on research and regulatory implementary dialogue, which cover regulatory aspects of and communication to regulators of safety case. We have a stakeholders confidence forum, which focuses on getting confidence within different stakeholders, especially in public, which is a really challenging thing for the moment. And we have number of groups in the past which contributed with information data knowledge management issues. Now we have created a working party fully devoted to these issues, and they support the safety case development. Also, we had a number of NA projects in the past, and they provided different type of scientific, technical, and some organizational inputs to the development of safety case. Economical aspects of deep geological repository has been discussed in a report of Nuclear Development Committee. We have support from database, chemical database, and future events and processes base. And all these things will be discussed in order to identify ways how new initiative, when it is established, how this all experience gathered within 20 years more can be adapted to the development of disposal of safety case for all types of disposal facilities, in order to make the process as much as possible universal, as much as possible unified. At the same time, we consider that process as part of global optimization of nuclear waste management programs. Next slide, please.
Could you please wrap it up, Vladimir? We're running long. Could you please
okay.
wrap it up?
So, thank you. How RWMC looks at this very previous vision of development concerning deep borehole disposal. This concept can be discussed as one of the other types of disposal facilities in future activities when this activity is established. We see some commonalities now. Both types are situated underground. The main barrier is host rock, and we see a lot of differences between DBD and GGR concepts, and different types: geological engineering, construction, operation, observation of after closure, safety provision, and many others. Safety case for DBD structurally is expected to coincide with the safety case for deep geological repository, and key elements are expected to be the same, as well as for all types of facilities. And thank you, Jeff. In your presentation, you demonstrated it very well. The content of key elements can be different with deep geological repositories due to specificities differ one type of facility from another. And I would say that even safety case for deep geological repository can differ from country to country, taking into account country specificity, different requirements. Safety case for deep geological repository can be used as a base for development of safety case for DBD, and experience gained in the NEA, RWMC, IJC is a good start point for elaboration of DBD safety case when relevant request comes from member countries. Next slide, please.
We're really going to Vladimir, let me interrupt you. We're really going to have to wrap it up. So please, a couple more comments, but we have to close out.
Oh, okay. Can I continue? Can I finish? Briefly, very briefly.
Please, quickly.
Okay. We see that we identified the main challenges, future direction, and we identified the most important thing are effective communication of safety case to all stakeholders, including public, and uncertainty management and communication of this management. Next slide, please. Perspectives regarding the geological DBD concept, as I said, first discussion in the workshop. Then when any members express interest, the potential creation of any initiative or discussion of this concept within any existing initiative can be discussed. The proposal on new activity would be presented to RWMC in 2022, and RWMC would decide. Next slide, please. And conclusions, the safety case is essential tool to support decision making. Internationally, this concept is incorporated in IAEA standards and other documents. Evidence of use of safety case could be seen by Finland and Sweden, and as I know, the US applied this concept in Yucca Mountain project. The key challenge remains is communicating safety case to all stakeholders. The basic principle and approaches to the creation of safety case for DGR can be applied to other types of facilities, including DBD. And the issues specific for DBD are to be studied in order to effectively adapt the safety case to be DBD projects. And next slide. Here you can see the sources of information, publications of the NEA regarding the safety case. And next slide. Thank you for your attention. Should you have questions, you can use this address to send your questions. Thank you.
Thank you very much indeed, Vladimir. It's encouraging two things, really. One is to see that the safety case approach for deep borehole disposal really is based on something that we've had for very many years now, and is not going to, although the components may be slightly different, the approach is going to be more or less the same. The other point, of course, was that you're opening up the opportunity for people to come to RWMC with ideas for joint projects over the course of the next year. And I think that's very encouraging. And when we talk, there's a bigger panel tomorrow afternoon, I think, looking at some of the potential projects that are kind of come up in the future. We go come back to that and perhaps have some ideas there. I'm well aware that we've overrun our original 90-minute slot. In fact, we're getting up to 2 hours now. So I would encourage our participants not to run away quite yet. We are planning to have a panel session where all of the panelists from today and tomorrow will be getting together at the end of the shorter set of presentations tomorrow. But just to wind up today, I'd like to look at what questions we're going to be asking. And I'm not going to read all of those, but I would encourage the audience to have a look at those and see whether they reflect some of the ideas and thinking that you've probably had about deep borehole disposal. And really to say that we'll be coming back to look at these tomorrow. And today I just want to take one of those and put it back to our panel. And the question there is number 2. We've had decades of development of deep geological repositories, and we've had regulatory cycles of right up to the point of view of construction licensing and operating licensing. So my question to the panel as a whole is, what do you think it's going to take to bring deep borehole disposal up to a similar level of maturity, if you like, with respect to getting it through into the regulatory cycle? I'd like to kick off just by asking Pat. I think you had an interest in speaking about that. So would you like to say a couple of words on that?
I'm sorry, Neil, can you restate the question? I just got bounced off and I just got back.
Oh, okay. It was the second question on our list of questions, which I think you'd had some interest in, which was, what do you think it would take to bring deep borehole disposal up to a similar cycle and level of regulatory approval as conventional deep geological repositories?
Sure. A successful demo project. It's hard to think of deep borehole disposal in the same vein as mine geologic disposal because we don't have a demo project. We've got lots of similar things, but that's why the work by the Australians is particularly inspiring. So there, a demo project.
That's a short, sharp answer. I like that. And we'll be hearing tomorrow from Deep Isolation that they've done one part of a demonstration. We're going to hear from the CSIRO tomorrow that there is a major project planned to do demonstration of a number of things. We know that in Sandia you are hoping to be able to do one in the States. I know my colleagues at Sheffield had also years ago talked about the need for a demonstration project. And I think all of the things that we're looking at now are coming to a focus now that in order to move forward with this, we're going to have to think about demonstration projects. That could be a really good point for our panel to think about for tomorrow. Before we come up to the second hour of this, I think I'm going to try to wind down for the day. We've got quite a lot of participants out there. We've got 150 participants who've been listening to what we've said today. I'd encourage you all to come up with comments and questions, and we'll address those, as I said, in writing. But please do come back tomorrow. We've got a very interesting set of additional presentations, some very practical things that we're going to be looking at, and I hope more chance to discuss them in the closing panel session tomorrow. With that, I'm going to hand you back to Thomas to close today's meeting, and we'll hope to see you all again tomorrow. Thomas.
Thank you, Neil, for driving us through these almost two very interesting hours of discussions. We've seen some very deep expert discussions. Tomorrow will be a little bit more practical with demonstration and first-hand approaches. So I have a little more to add, as invite everybody, do come back tomorrow and prepare your questions for tomorrow, as tomorrow we'll have much more time, and we will be also to promote some of the questions from written questions to oral questions in our discussion. So thank you again, and see you tomorrow.
Yep.